Okay, well, good morning, you guys. We're going to be taking a look at some specific heat problems. Q equals M times C times delta T. We looked at some of these earlier this week on a couple different labs we did. On the coffee cup calorimeter lab, we did Q equals MC delta T to see how much heat energy was being absorbed or given off by the reaction going on in solution. We also did it with the Flame and Foods lab to see how much heat energy was being absorbed by the water, so we could kind of figure out how much heat energy was being given off by the food we burned. So this up here at the top is your main basic reaction. Q, of course, is heat. M is the mass of the substance that's either taking that heat in or giving it off. C is the specific heat, and that's a constant that is different for every substance. You know, we looked at water. Water's was 4.18 joules, which meant that to raise the temperature of water, you have to add 4.18 joules, and that would raise 1 gram of water by 1 degree Celsius. And then delta T is changing temperature. Now, something you might add up here, to find delta T, that's going to be equal to your final temperature, T sub F, minus your starting temperature, T sub I. Okay? So if you need to find that, that's how you find that. What I wanted to do today is I wanted to look at a few of the problems on this paper, just so you could have some examples to look back on as you work the rest. Now, if you're given a problem that's just asking for Q, that's easy, because all you have to do is identify these other three variables and multiply them together. It's when they start asking for some of these other variables that it might get a little bit trickier, but I'm going to show you a way to make it a lot easier on yourself. So let's start by taking a look at problem number 1. Okay. Number 1, the specific heat of platinum is 0.133 joules per gram degree Celsius. So how much heat is absorbed when a 10-gram piece of platinum warms from 100 Celsius to 150 Celsius? So let's identify, first of all, what does the problem want us to find?
Well, to find how much heat is absorbed.
Okay. So it's wanting to know how much heat is absorbed, so we're looking for Q. I'm just going to kind of jot Q down in my margin right here, and I'm going to circle that one so that I can remember later, hey, that's an example we worked, so if I need to find Q later, I can go and see how we worked this one. Okay, so I'm going to rewrite my entire formula. Q equals M times C times delta T. Always start with your same basic formula, and then start plugging in numbers. So since I'm solving for Q, what's my mass?
12.1
And that is not mass. Okay. T there is grams, right? Mass is measured in grams, so that's my mass. It's going to be 10. C is my specific heat, so what's the specific heat in this problem?
120 degrees Celsius.
That is not what that says.
50,
That, okay. Yeah, the clue there when I'm asking what's the specific heat is this part that says the specific heat is. Yeah, context, my guys. Okay, so 0.133. And then I have to multiply by delta T. Delta T, they don't flat out give to me. They give me 2 temperatures. So which one of these is going to be the temperature I start with?
100 Celsius.
100 Celsius. And my clue for that is it says it's going from that to this other one. So it's going from my TI, initial or starting temperature, to my TF. And we set up here that delta T is TF minus TI, so it's going to be 150 minus 100. So what is 150 minus 100? 50. Positive 50. So my delta T is going to be 50. No, I don't have to divide by anything. Literally, I am taking this times this times this. So at this point, grab my handy dandy calculator, and I just type in 10 times 0.133 times 50, and I get 66.5 for an answer. Okay? Now my question is 66.5 what? Because we're looking for heat energy, we're looking for Q. So what is heat measured in?
Joules.
Joules. So my answer is 66.5 joules. I'm going to box it or circle it or something so the teacher knows that that's my answer. And I'm going to move on with life. So that's one of the easy ones. So show me fingers right now. How do you feel about that? I'm seeing 5s and 4s. Okay, cool. All right. Let's check number 2 and see what they want us to find number 2. What are they looking for in question 2?
How much energy used from the one.
Okay. So again, they're looking for Q. So I'm going to write the Q out in the margin there. I'm going to skip 2 right now because I know that I can go work it a lot like I worked 1. How about number 3?
How much heat is used in grams like Celsius?
Number 3?
Oh, wrong one.
Just looking for what do they want me to find on number 3.
Temperature change.
What is the temperature change? So on this one, this is a little bit different. They want me to find delta T. So I'm going to work this one as an example of what to do when they want you to find something besides Q. So I'm going to start by rewriting that same basic equation, Q equals mc delta T. Now this time though, I'm trying to solve for delta T. So instead of plugging in numbers, what I want to do here is I want to change my formula to where delta T is by itself. So in other words, what I'm going to be doing is I'm going to go ahead and algebra this formula to isolate delta T. So if I want to get delta T by itself on the right-hand side of the problem there, what do I need to do to get rid of that M and that C? What's being done over on this side? Multiplication. So it's being multiplied by these two, so how can I get rid of them? Divide. And since it's algebra, I'm going to divide both sides of my equation by M and C. Okay? On the right-hand side of the equation, M divided by M cancels out. C divided by C cancels out, and I'm left with delta T, right? So now all I have to do is do Q divided by M and C. So now I can plug these in. What is my Q? What is my amount of heat that was added? 100 joules. So 100 is on top. Okay, what's my mass? 20 grams. Okay, and what is my C? What's my specific heat for copper? 0.385. Okay, so then I go to calculator. So I'm going to go, now a couple different ways you can work this in your calculator. I've told you before that when you've got something like this, you multiply by everything on top and you divide by each thing on the bottom. So I can do it by going 100 divided by 20 divided by 0.385. Or another way that I can look at that is I can go 100 divided by those times each other, but if I do that, then I have to use parentheses on my calculator. So I can go 20 times 0.385, and it gives me the same answer. But you have to use parentheses if you multiply by that, because otherwise it's going to think that you're putting that up in the numerator, and it's going to give you the wrong answer. Okay, so whichever way you do it, I get 12 and a whole lot of change. So I'm going to round that out to a couple places. I'm going to call that 12.99. So if it's asking for temperature change, what's my unit that temperature is measured in? Not joules. Okay, degrees Celsius. That's how much it changed. Now that's an example of a tricky problem. So show me fingers, 0 to 5. How you feeling? Still getting some solid 4s. And a 5. Cool. All right. That's a great place to get lost, though, so if you have any questions, please ask me. Like, why did you, or how did you, or how did you know to, anything like that. All right. Let's continue on down. Let's look at number 4. What does 4 want us to find?
How much heat is released?
Okay. Frozen for how much heat is released, so that's another one where we are solving for Q. What about 5? What does 5 want?
Calculate the energy transfer when raised.
Energy transfer. So out of our different variables, Q, M, C, or delta T, what is that? What do you think? You think C? C is specific heat. Now, that's a decent guess. Let's take a look and see what else they give us here, and maybe we can narrow it down. So, what is 16,000 grams?
It is the mass.
That's mass. Okay. Raising the temperature of that by 3 degrees Celsius, so what would that be? No, it doesn't say that that's the specific heat. That's delta T. So we don't have Q or C apparently, right? So do we have enough information to solve this problem? Kind of yes, because look what we're raising the temperature of. Do we know what the specific heat of water is?
4.18.
4.18 joules per gram per degree Celsius. That's exactly right. So I can come over here and I can go ahead and write that C equals 4.18. And if I didn't happen to remember that, it is up here on number 2. You take a look right there. Okay, for water. So if we've got C, M, and delta T, then what is energy transferred? What's the only other variable we don't have there?
Q.
Yeah. Remember, Q we talk about as being heat, but heat is just a form of energy, right?
Yeah.
And all energy can be measured in joules. So we're still looking for Q on that one. How about number 6? What do they want us to find?
How many joules? How many joules?
Okay. So what unit would that be? Or what variable?
That would be the Q.
That's Q again. So we're going to skip that one. How about 7?
Calculate the specific heat.
Oh, that's different. So it wants us to find specific heat. What variable is specific heat? Yeah. And actually, it's not a variable, it's a constant, but they want us to calculate the constant on this one. So let's work that one together. Okay. Calculate the specific heat of titanium. 43.56 gram sample absorbs 476 joules as its temperature changes from 20.13 Celsius to 41.06 Celsius. So, like I always do, I start by rewriting my main formula, Q equals MC delta T. Now this time, I'm trying to solve for C. So before I plug in numbers, I'd like to algebra this formula. How can I get C all by itself? I'm going to be doing some division. What am I dividing by?
M.
And? Yeah. And since it's algebra, I divide both sides by M delta T, right? On the right-hand side here, mass divided by mass cancels. Delta T divided by delta T cancels, so I'm left with C, which is what I need. So to solve for C, it's just going to be Q divided by M delta T. So now we can plug in numbers. What did we say my Q was? What's my energy? 476 joules. So it's going to be 476 on top. Okay. What's my mass? 43.56. Okay. Delta T we have to calculate, so we need to know which of these is my starting temperature. TI?
20.13.
Okay, that's my TI. It means that that's going to be my TF. So if delta T equals TF minus TI, so it's going to be 41.06 minus 20.13. Somebody want to crunch that for me and tell me what that is? 20.93. Very good. Bless you. There's my delta T, 20.93. Okay, great. So now we'll calculator this. So I'm going to do 476 divided by 43.56 divided by 20.93. What was that up there? Did I put something wrong? 3. Oh, I did. I swapped a number there. Let's try that again. 476 divided by the right thing this time. 43.56 divided by 20.93. It was close, but there's my answer right there. So what do you think we ought to round that to?
0.52. I can't really see.
Okay. Can't really see?
Yeah, 5. 0.5.
Looking at the other values of specific heat, they all go out to 3 decimal places, so I'm going to go ahead and make it 0.522, just because. So 0.522. Now, what are my units for specific heat? And this one is the big complicated one. Look at how it's expressed on some of the other problems.
Joules
It's part of it. Joules per what?
per gram.
Per gram degree Celsius. Yeah. Because again, specific heat tells us that for titanium in this case, if I want to raise the temperature of 1 gram of titanium by 1 degree Celsius, I have to apply 0.522 joules. Okay, which is a lot less than water. Titanium heats a lot more easily than water does. Okay, let's look at the last few. Number 8, what does it want us to find?
What is the final temperature of the?
That's interesting. So we're looking for TF this time. So number 8 is going to be a little bit of a tricky one. I'll kind of put a little cloud around that. We're not going to work it, but the way I'd work this, first of all, is I'm going to try and find my delta T. Okay, so I'm going to start with my main formula, and I'm going to solve for delta T, just like what we did up on number 3. Remember how we changed it? Delta T equals Q over MC.
Yeah.
Okay. Once I've got my delta T, then I'm going to take this other formula right here, that delta T equals TF minus TI, and I want to try and rewrite this to solve for TF. So this time, how can I get TF by itself on one side of this equation?
Adding
Okay, what am I adding to both sides?
the final in the starting temperature.
Exactly. So I'm going to add TI to both sides. Over here, negative and positive TI cancel. So it's just going to be my starting temperature plus my delta T will give me the answer I want. Okay, so there's actually 2 parts on number 8. Don't forget to do that second part. What does number 9 want?
That's what the specific heat.
Okay, so that one is also having us look for C. How about 10?
Fifth final temperature. What is this, man?
This one we're trying to solve for M. That's different. I'm not going to work this one with you because I want to see if you can rewrite your starting formula to get M by itself. Just kind of look and see how we rewrote the other ones. And what about 11? What do we need?
How many joules per energy are you?
Okay, so what is that?
That is Q.
Excellent. Okay, so before I turn you loose and say, hey, go work on these other ones, let's do one more. Does anybody have any questions? And one more show of fingers. How are you feeling about this? Good deal. Lots of fingers there. It's not too bad, guys. Just do what you can with it. If you feel like you're getting stuck, feel free to ask for help.